All right, folks. Welcome. Last week we watched a couple of recorded videos on the thin wall torsion and examples for those, and then a little bit of our elasticity method, which is also a preview for the 4612 class. We tried it out with a circle, which we already knew the answer to from our geometric circular torsion theory, and that worked out. And then for the homework, we're going to try it with an ellipse. We also tried that triangle problem in class to see where the non-circular solutions came from. So before we get into the homework reviews, was there any pressing questions people might have had about those two recorded videos? Anything to clear up? Okay, out in TV land, anything? All right, you can also table that for after the exam. I understand people don't want to think about it for a little while. So let's jump over to our two homework sets, and we're just going to go through all those problems. If you have any questions along the way, then just feel free to shout out, okay? So first problem here, we're looking at this composite deck house patch, like we maybe briefly talked about before. After the nuclear cruiser craze and the realization that it would cost too much money to build a fleet of nuclear-powered surface ships, even though they could steam along with no refueling, they realized, well, we're still going to need other provisions and things like that, and we can build a conventionally powered cruiser for much less money, and we can build more. So they took the Spruance destroyer hull, and to pack all that Aegis equipment in, they had to make the superstructure out of aluminum instead of out of steel. So that 5000 series aluminum had some sensitization issues and stress corrosion cracking issues. And to help fix, at least on a temporary basis, those issues, they started using some composite patches. So here we've got a parallelogram shaped composite patch. It weather seals a crack in the superstructure above the deck house there. So maybe like 05, 06 level around there. And we've got loadings under the ship motions. We got a traction of 1000 psi going straight up and down, and then 500 psi at 60 off of vertical or 30 off of horizontal. And we got a 20 by 30 patch size here. Right. So it's going to run very similar to what we did in class, except for this time, we're going to already have the X surface ready to go. And we need to create a surface that's normal to wire. Would somebody mind going to half light on the lights back there, just so we could see a little better? This one's drawn with the fine point pen. So, all right. So we need to take a slice. We either need to take a slice across at the top or across at the bottom, whichever one is going to be more convenient for us. If I take a cut right here, I've got my y normal face, happens to be going down in this case, so I will get a face that's minus y, or I could take a cut at the bottom and get a plus y face. All right, so either one of those is okay. We wouldn't necessarily want to cut it anywhere in the middle, because then we end up with four sides, and that's just more stuff to add. All right, so you can take this one or that one. Either way, going to work out the same. So because I took the top slice here, my y is pointed down, and always trailing it by 90 degrees is going to be my x. So my minus y face is going to have a shear traction that goes in the minus x direction. I got minus y down, minus x to the left, or if we cut it from the bottom, we're going to have positive y up, and trailing it by 90 degrees would be positive x. Okay, so here's our tau xy, here's our signal yy. On the top surface, I'm not normal to any coordinate direction, so I can't peel any loads directly off of that. The right-hand side, or the left-hand side on the bottom, is already perpendicular to x. So I just have to take that 500 and cut it into two components. So I got cosine and sine for 60 degrees, or cosine and sine for 30, get 433 on the horizontal and 250 on the vertical. Since we're already on the x face, the horizontal piece is going to be x face, x direction. So there's sigma xx. X face and y direction, positive and positive, would be up. So that matches. So we get a plus 433 and a plus 250. We didn't really have to do any work for those. Since I've already got tau x face y direction, my tau yx we know is symmetric. So I could sum forces in x and get the same value for tau xy using that bottom face tau there, but we don't have to. All right, we've already got it from the right-hand face, and we know they've got to be equal and going in those perpendicular directions like that. We don't know sigma yy, so all I've really got to do is take this block right here and sum up all the vertical forces. So first force that we've got going vertical is that 1,000 psi. All of it's going up, and we just need an area for it. The shear force on the right-hand side is also going up. So we need an equivalent force out of these arrows right here. And then we've got our sigma yy on the bottom. So all these vertical arrows here. These are our threes. And then we want to imagine this triangle like a wedge, something akin to this. Fairly good straight line work there. So we've got surfaces, and we can just assume a unit depth direction. That's going to be the simplest way to do it. So we'll just assume it goes 1 unit into or out of the page. So we're talking about, for that 1,000 psi, this surface, this diagonal of the wedge, that's the area over which the 1,000 goes. All of it's in the y direction, 20, and we'll just assume a unit depth. You could assume any depth because it's all 3 surfaces are going to have the same one, so it'll cancel off. 1's the easiest number to divide by or multiply through, so we'll just put 20 by 1. Then we've got the shear. That's going to be over on this right-hand face. That's going to be this face back here. Height of 10, and assume that same depth. And I could see, since they're equal to 0, I could have multiplied by any depth. And then on the bottom, I've got this 17 1/3 inches, and then I've got 1 inch of depth. And that's going down, so it's the only one that gets the minus. Okay. All right, so that takes care of all the forces in the vertical direction, and we just solve for sigma yy. We get 1299 or 1,500 if we're rounding a little bit more. We could check tau xy by summing those x forces. We'll still come out to the same thing. The only thing going in x is the 433, and then the tau xy on the bottom face. The 433 on the right, the tau xy on the bottom. Those are the only horizontal components we have, and it also comes to 250, just like we thought. We're doing a plane stress because the patch is thin in the z direction, so all those z stresses are 0. So here's our full state of stress. We've got a plane stress state because everything on this z row and or z column, because it's symmetric, is going to be 0. We could also shorten it to a 2 by 2. So there's our state of stress on the volume element cube. We can use our shortcut. Anytime that these 2 shears are 0, here and here, this formula is good. Even if sigma zz has a value other than 0, it's a principal as long as the rest of the row is 0. All right. So this is good, definitely for plane stress, and also for any case where z is a principal. So we got plus and minus on that radius component, and here's our average stress. Comes out 1366 and 366. And our third principal is sigma zz. In this case, just happens to be 0. Our principal angle is either going to be minus 15 or plus 75. When we started out, we had 1299 going up, and we had 433 horizontal. We're only tilting at 15 degrees. There's a good chance that the bigger number is going to go in the more vertical direction and the smaller number right here. But we can also just plug in sigma x prime from our transformed formula. So if we jump right over here and grab from the stress and strain, let's get our stress transformation. That's going to be here we go. All right. So for 2D state of stress, I can plug in right here for any angle. So if I put in minus 15 and I put in my xx, yy, and my tau xy, this sigma at the new angle minus 15 degrees, that's going to come out as the 366. And then if I plug in 75 degrees, which is the other principal, that should come out the other number 13. You only have to check one of them because once you find one of those surfaces, the other one is going to be perpendicular. So if I plug in 75 degrees, I'm going to get this number on my sigma prime. And if I plug in minus 15, I'm going to get this. Right. Max in plane shear is going to be the difference of those two divided by 2, and that's going to be 45 degrees away from both of those faces. So there's tau max in plane, and tau max absolute is just the biggest difference of these two. That's going to be the 0 and the 1366. So it comes out 683 right there. All right, anybody have any questions about that one? You can also get this principles using the eigenvalues. We'll get same thing. All right, for our second one here, we've got a cube with known values for all the stress components. We need to peel those off there and put them in the 3x3 matrix, then get our principles, construct our Morse circles, and then get those max shears. So for this one, it's just a matter of identifying each face and then what direction the stress is going. First one is our X face. That's just going to be whatever's normal to X. So that's going to be this guy right here. And then that gives us our first letter for the subscript. So this is going to be the whole first row of the stress tensor. And then I'm going to have an X direction, a Y direction, and a Z direction. That's what we have to match up with these arrows. All right. So sigma X face, X direction is going to be matched up with that 10. X face, Y direction. I see the 5's going down, Y's going up. Positive X face, positive Y. So sigma XY or tau XY, I could see is going against this number. So it goes against the sign convention. That means we're going to get -5 there. And we don't have anything moving out of the page on that X face. So XZ is going to be 0. So we got 10, -5, and 0. That's going to give us our first row and also our first column because it's symmetric. So we got 10, -5, 0. Then we go up to this Y face right here. Let me get a different color for that. We go blue. So up here, Y face X direction, 5's going against it. And I can see those two are tail to tail. Remember, XY and YX should be the same value and the arrows will go opposite directions so this doesn't spin around Z. So that checks out okay, -5. Y face Y direction, 7's going the other way, so I get a minus there. And I don't have anything pointed in Z right there. And since XZ is 0 and YZ is 0, I'm expecting ZX and ZY to also be 0. And when I come down here to this face, Z face Z direction, there's my 4. I've got nothing going in X, and I've got nothing going in Y on this Z face. So Z, I can see, is a principal direction, all right? As long as these two shears in the last row and column are 0, we can use that shortcut form, all right? So sigma ZZ is going to be one of the principles. Let's pull that off right there. And the other two are going to come from our shortcut. We can also take this and throw it into eigenvalues and get the same 3, all right? So 11.3 minus 8.3 and 4. Does not matter what you label 1, 2, or 3. Oftentimes, if it's a full 3D state like this, they'll go largest to smallest or most positive to most negative. But you can also make 1 and 2 the in planes and make this 3. 1, 2, and 3 doesn't have any significance. It's just a no. So we've got our +4 right here. We've got our +11 right here, and we've got our -8 right here. And all we really need to draw the circles is those 3 spots. Those are our diameter points. So we connect the circles, and that's what we've got. Our in-plane circle is this one because our 2 shortcut values came from right here. So that's going to go here and go here. That means this outermost circle is the circle that contains our XY plane. That means X is going to be found somewhere on there, and so is Y. This is really the P1, P3 plane. From those 2 principles, that's what forms. It just happens to be that X and Y face are in that same plane. Okay. Likewise, the P1, P2 circle is rotating between those two values and rotating about that P3 direction. And the P2, P3 circle rotates around the P1. Right? So for us, P2 and Z are the same. And that means we can rotate around to get X and Y and the other two principles on this big circle. Now our X and Y was located, if we wanted to mark it, at 10, negative 5. If I grab for that face, green. Yeah. Okay. So 10, negative 5. I go out here to 10, that's almost all the way over, and negative 5, maybe we end up somewhere up here. So this is my X face right there. And straight across from it will be Y. What did we have for Y? Well, Y came out at -5, -7. That's for YX and YY. So -7 on the horizontal axis. And then I see about 5. So 5 out of max shear of 9 is going to be about halfway, maybe about right. We can see those are just about right across from each other. Now, remember this sigma and tau, okay? That's for any given face. Here's sigma, and tau leads it by 90 degrees. So at X, it's going to look just like this. We read the coordinates right off of there. All right, 10, negative 5. That's exactly where we go. 10, and then remember tau's positive up, or positive down, so we go up there to negative. Now, when we get over to the Y face, this is just a continuous rotation. Center's probably right about here. So when I'm reading my angles, here was my sigma average from the shortcut, somewhere right there. My angles are going to go like this. Here's my 2 theta, starts right here. It always starts at X, or from horizontal, is our traditional start for theta. But a relative angle is between all. When I rotate this 90 degrees, my sigma is up here. My tau on the Mohr's circle points to the left. Okay. So here's sigma and tau from the 2 coordinates that we have. If I look up here, that's going to be -7, 5 in the rotating system. Remember, this is like a sigma prime and a tau x prime, y prime, right? This is like an x prime to any old angle that we rotate to. And that's always true on the Mohr circle. And we're looking at this like it's an x prime, y. So this is a rotated. And because we've rotated from X up to Y, we go halfway around the circle. 2 theta equals 180. And I can see that that comes out positive. So even though tau YX is at -5, on the circle, we're always just taking a thumb and an index. So if my thumb is up at this Y face here, my index is to the left. So I get -7, 5 on the circle. So there that is. Whereas our original stresses, sigma YY is going to be this way. And tau XY, if it were positive, over here, right? So that's why we see a positive sign on the circle, because the tau's just spinning around. So it always leads sigma. There's our spots. And then max in-plane shear is between the 2 we got from the shortcut. So there's that, or whatever circle X is on. So that's our in-plane. And that also happens to be the biggest circle, so that's also the absolute max. Anybody got any questions about that, or the Mohr circle in general? All right, let's take a look at the next one. Here we got some dynamic forces, maybe something multi-axis spinning, and through some measurements of strain and converting over stress, we got a stress distribution for this body. So we know how the stress is changing inside the body, and we want to figure out what kind of body forces would create this stress distribution. All right, we see they're just a function of position. That means they're changing in there. That means we got some tumbling on different axes, creating some acceleration. So we've got our X stresses up on the top row, Y stress on the middle, Z stress on those. And our basic stress equilibrium equation is what we need to employ for this one. So if we go to the summary of all the stress stuff, there's our equilibrium equations. Looks like we just need a partial derivative with the column that we're in. So xx with x, and then we move over to the next column, xy with y, xz with z. Right. So just take derivatives one at a time as we go across the column, plus the body force is equal to 0. And that's how it has to work out for the whole body to be in equilibrium. So we just need to take those derivatives, go across the top row, we get this, this, and this, plus body force in x. So we can get that as a function of position. Same thing, we can go across that middle row and just take derivatives per column. X for the first column, y for the second, z for the third. And same thing on the bottom. So now we've got our body forces as a function of position. And then at any given spot, say at this location, we can just plug it in. We'll get our components and our total body force. This one a little more on the abstract side, but essentially we're just exercising this stress equilibrium equation, all right? This is always true if we've got a continuous field of stress in the body, and we derived this purely from statics. Remember, we had the little cube, and in 2D, we did no rotations, no summation of forces in x equals 0, summation of forces in y equals 0, and summation of rotations equal to 0. And that's how we got these first two, and then we just expanded it. So this guarantees that our body is in static equilibrium. All right, let's take a look here. We've got a known state of stress in x, y, and z. So our loads, some perpendicular angles, and works out to what these stresses show right here. And then let's say we find a crack, and that crack face is opening on this face right here, right? We find some flaw in the material, and it's on a face that's perpendicular to 2, 1, minus 3 for the direction. So 2 to the right, 1 up, and into the page by 3. So we need to figure out what are the stress components on there. What's the sliding stress? How much stress is shearing on this face? And then how much, more importantly, if it's a crack, how much is pulling open on that face, all right? And we'd like to know, is it tension or compression in there? So for that, we can just use our traction vector. For that, we're going to need the state of stress. Gives us another little chance to pull off. So we got 20 going in the x direction on that x face. We've got 10 going in the y direction, and we got 10 going against the z direction. So 20, 10, and minus 10. We look up on the top face. I've got 10 going in x, 30 going in y, nothing going in z, so 10, 30, and 0. And note that if I look across this mirror line, everything's the same. And then on the bottom row, I've got 10 going against x, so minus 10. Nothing going up in y, and then 50 going in. So minus 10, 0, and 50 going with the negative. And we want to figure out what the tractions are on that 2, 1, minus 3 direction. So we make a unit vector for that size. And this is just a projection of that stress cube onto this one normal face. So we go through there, we get 21, 13, and 34. Those are still in our x, y, and z directions. All right. So I have the components of the stress, but they're still in the original coordinate direction. It'd be nice to know what's on this face and what's perpendicular to that face. All right. So here's my traction vector. It might be off, say, this way or something like that. Or it could be, maybe I'd draw it a little bit more that way. Artistic license on that one. They're all positive, so it's probably coming out somewhere out. So we've got the components, but we need to know how much of it is on this face and how much of it is perpendicular to that face. So the normal, that one that we already came up with, that's going this way. I want to project this traction that's in X, Y, and Z and figure out how much of it lands on here. So I want to know how much of that blue one is sitting perpendicular to the face. Positive if it's out, and we could get a negative, which would mean we get compression. And then some other part of it is going to be along this face. That's going to be sitting just on this surface down here. Okay. So the easy one to get is actually the normal stress. We can just do the dot product of the normal and the traction vector, dot those two, and that's going to tell me what lines up onto that normal arrow, onto this element. So we dot those, and I see I get a negative. So from a crack perspective, this is actually good. It means we've got compression on there. Crack won't grow. We'll get crack closure on that case. So the sign is very important on this one. This one tells me that I've got compression across the surface. If I get a tension, I know that could be trying to grow the crack. Now the shear one, all I'm going to get is a number for that. I know that somewhere around this 360 degrees, it could be right this way, could be this way, could be that way, could be that way. It's just somewhere on that surface, all right? But I'm going to get it through a difference of squares. So I get a magnitude, and I don't know which way it's pointed, but I do know that's what's shearing on this surface. And it comes out at 41. So I have a pretty high mode 2 shearing load, but on mode 1, I've actually got compression, so that crack shouldn't be growing. All right. So on this one, we took a regular stress state XYZ, we projected it onto a face, and then we turned it into components that are in or out of that face and along or parallel to that face. So normal and tangential. Anybody have any questions on that stuff?
I've got a question. Can we go back to number 3 for a second?
Yeah, sure.
All right, so our equilibrium equations, you have something called the body force, which is that Fx, Fy, and Fc.
Right.
Is that I guess I'm trying to get the intuition of why the derivative of a stress with respect to
Okay, so
um
these body forces are going to be on a per volume basis.
okay. All right. I
We
think that clears it up. Yeah, because I was thinking, why would a derivative of a stress give you a force
so what these actually link to
per unit volume? Okay.
is to a set of accelerations. Those could be centrifugal, they could be ship motion, they could be some sort of aeroelastic loading, but they're just an acceleration on the body. All right.
Okay.
So if we're thinking about the way we could think about this, so we know that force equals mass times some acceleration, right? Right. If we take a force per volume, which is what these loads are, take a mass per volume, and essentially what this is, if you wanted to know the accelerations on this body, you divide by whatever the material density is to get acceleration in X, Y, Z. So it's going to be the acceleration, these represent the acceleration times the density of the material.
Okay.
So these three values over here are going to be this force per volume, and they represent these three. If you already knew what the ship motions were or the accelerations on the body and you wanted to put those in to work toward getting the stresses, you just take the accelerations times the density for the material.
Okay. Got it. Thanks.
Yep. All right, so let's take a look at number 5 here. Here we're going to exercise that strain compatibility condition. And in class, we took some time and talked about that one, that if we know what the displacements are and we take derivatives down, we'll always get the right strains. But more often than not, we're measuring stuff with strain gauges, unless we do the digital image correlation, or put some strain gauges on there. So we know what the strain is at different spots. And that means we're trying to integrate up to get our displacements, to get to U and V and W. And when we integrate up on the same derivative, those normals, and we integrate up on the opposite derivative, those shears, we can come up with different values because we only see the dy part or the dx part or vice versa between the normal and the shear integrating up. So to make sure those come out the same, we take a few derivatives down and we set this equal. So two opposite derivatives with epsilon xx, two opposite derivatives with epsilon yy needs to equal to a same and an opposite on the gamma. And if we take those derivatives right on here, we'll come up with the exact same stuff using these three. Right? So it's going to help us solve for u and v. Now what we've got going here is we've got displacement here with terms of some constants a and b, and then separately through some angular measurements, we've got shear strain. And we just want to relate those two constants together. So all we're going to do is exercise that equation for strain compatibility. We go down one same derivative to get epsilon xx and yy, so they're right there. And then we need to take two opposite derivatives of this one, two opposite derivatives of this one, and there they are. And then we take one derivative each on the shears. So what we're left with is some functions of x and some constants on the left, and some functions of x and some constants on the right. If this is good all the time, no matter what I put in for x, then the coefficients have to match. So 4a naught has got to equal 2c naught. And likewise, no matter what I put in for x, 2a1 plus 2b naught has to equal to c1. All the constants have to equal and all of the extra. So the coefficients essentially have to match up. And we get that. We can also double check by just looking at du dy and dv dx versus gamma xy, taking a derivative down and comparing those directly, and we can see this c naught on the x squared y matches up to 2a naught on the other x squared y, and the c1 over here, got an xy that it's prefixing, matches up with the 2a1 and the 2b. So we can look at that a couple ways, either strain compatibility or just matching up opposite derivatives. Now for number 6, here we're looking at access hatch. Tends to get stuck when we're underway. So the next time we're in port, we slap a strain gauge rosette on there. It's going to be the most popular one, a 04590 gauge. And we get the three readings. We get 1200 on F, we get 1500 on that diagonal one at 45 degrees, and we get negative 700 on our epsilon H. And just like we saw in our course notes here, it's a little touchy today, we can take any three gauges and they're on specific angles. So if we start one at 0 and 90, one of them is going to equal epsilon xx, the other is going to exactly equal epsilon yy, and then we just need to solve that 45-degree one and get the gamma, the one that we don't. So let's see how that plays out. Epsilon f is horizontal, so it is the xx strain. Epsilon h is yy, so that's definitely the vertical strain. And then this is what's left. I measured the normal strain at 45 degrees, so I throw in there, I get a half and a half, and also a half here. And the only thing I don't know left is gamma xy. So I can solve for that one. I get 2500 microstrain positive. Right? Now we want to know how the diagonals are changing. How is this AC length changing? How's that BD length changing? From geometry, they're both 36 if it's a 30 by 20. AC is going on a downward angle, so we call that minus 33 degrees, and the other one up 32. If I already know the three components, I can go back, and for any angle, I can get the normal strain, right? So if I plug in positive 33, and I know these three coefficients, then I'm going to get the epsilon along that BD direction. Or at minus 33, I'll get the AC. And for positive 33, I'll get the BD. Right? So we'll get those two strains. And once we plug those in, we get minus 538 across the upper left to lower right diagonal. And then we get positive 1769 on the BD direction. Delta is just strain times original length. So displacement, it's getting shorter in that AC, and it's getting longer in that BD diagonal. So if we wanted to fix this for the next time underway, I can see AC is getting shorter, BD is getting longer. We'll just go in with the grinding wheel and take a little bit off of here, take a little bit off of here, and we shouldn't be stuck. All right, did anybody have any questions about that?
Question about stress. So when do we care about the epsilon XY and not gamma XY?
So gamma XY and epsilon XY, one's just twice the other number. The gamma XY represents the total angle change. All right. So that's why it's called engineering shear strain. We like something that relates to the everyday world. Gamma XY is the total angle change. How much does it change from 90 degrees at that corner there? And our epsilon XY is just what we need to put into the 3x3. It's half of gamma. I like to think about it, we split it. We split half of gamma here and put half of gamma here. If we want to do any rotations, like use our eigenvalues, eigenvectors to get principles and things like that, we need to have it in as epsilon XY here and here.
Okay.
We're thinking about it in geometry, the total angle change is going to be what gamma is.
Okay. And then like when we do Hooke's law and like convert from stress to strain or strain to stress, would we use epsilon there too?
Hooke's law usually expresses in gamma. So
Okay.
when we're talking about picturing something or Hooke's law, we usually see gamma. If we have to do any rotations, then the formula using the L epsilon L transpose that uses the epsilon X1.
Okay.
In fact, if we look over here, if we're doing the stress transforms, this came out as 2 tau xy right here. And in the 3x3, it would be 2 epsilon xy. So that's why we see only a gamma right here. And if we go back to our stress,
Yeah, it'll be
so
2.
yeah, keep in mind what we just saw there was a little bit touchy. So see here, you could see that came straight out of the 3x3 is a 2 tau.
Okay.
And in our case, there will be 2 epsilon xy, but we see just gamma in that strain transfer.
Okay. All right.
Now, one other way to think about it. So bear in mind, we got 2,500 for gamma. That's a positive angle. 1,200 and negative 700. So let's just draw this out real quick and see what would happen. Okay.
Okay.
Video, and I should have works one. All right. So let's think about the XX part first. All right. I know that I'm stretching out positive for epsilon XX. So it should get longer in this direction. That makes sense. And then for epsilon YY, I'm getting shorter. So let's apply just epsilon XX and epsilon YY. We're into this purple shape, dotted shape here. Okay. So epsilon XX was a stretch, epsilon YY was a shrink. I know I'm crunching it this way and stretching it that way. Now, our shear was positive 2,500. So regardless of the exact distance, I know a positive shearing turns into this kind of a shape. We saw from positive x-axis, we go up. From positive y-axis, we go to the right. That's a positive. So I know that my shear is going to make it go this way, over to the right. And on this axis, it's going to go up. So let's say it ends up here, and we're going to exaggerate a little bit. And then I'm going to end up maybe something like that. All right. So there's going to be a final state. The red one's just XX, and then I add YY, and then I add the gamma. This is my final deformation just by direction, okay, with not any accurate numbers in there. I can definitely see that this side looks like it should be smaller, and we did get a negative strain and displacement for that. And this one looks like it's longer. So this one came out with the plus like we thought it would. This one came out with the minus. So if we look at the original epsilon XX, the effect from epsilon YY, shrinking that red box down. And then if we add in the gamma part, which is a positive shaped parallelogram like this, it does look like these two corners, B and D, have moved outward from away from each other. If we fix this spot, this one's definitely moved farther, and A and C have come closer together. Right. So if you just want to think about it purely in terms of geometry, this is what you got. And you can work that out. You could take epsilon XX times this length and get how far it went here. You could take epsilon YY times the height, and you could get that. And then you could use gamma and some tangent stuff and figure out how far the little green movements are right here, right here. So this could we could figure out where this is, some coordinate, and then say this is 0, 0, and work out that distance L final also. But just from the directions, positive for the horizontal, negative for the vertical, and then a positive shear, I can see those two corners got farther apart. So these are the problem areas that I need to grind out and make a little room.
Okay. Yeah, because that's actually I was trying to picture that the first time I did that, I tried that problem. I didn't do the rotation, and I was trying to do something like that, but then I ended up just doing the rotation because it was a little bit easier, but okay, yeah, that's starting to make sense.
Yeah, so remember, if you're going to work it out just geometrically, you'd have gamma over 2 here and gamma over 2 here. That's essentially your tangent. So I could take this original height, multiply it by gamma over 2, and that would give me this distance. And I could take this horizontal length, multiply it by gamma over 2, and I could get this height change for this line on the parallelogram and this line. And of course, these will move the same distance. They'll both tilt the same. So this distance out here and this vertical distance off of the original spot, it'll look something like that.
Okay.
So you can work that all with geometry. It starts to get a little, if it's principal, you can make a rectangle into another rectangle. Once you start tilting it, adding up all these things and keeping track of them gets a little tough, which is why the formula takes care of it for us. The epsilon prime at any angle will just get us strains no matter which way we want to look.
Right. Okay.
All right. Any other questions about that? All right. Let's jump to our next one. We're going to stay on that same access hatch problem. And we think about those panels, all right? This was to get into the uptake space, maybe right next to the ramp on an LHD or an LPD. You've got those access panels to get into the uptake spaces. So we know those panels are fairly thin. We take this plate off. It's got 20 and 30 inches, but it's maybe a ½ inch thick or quarter-inch thick or whatnot. So we can assume a state of plane stress for a panel or a hatch or anything like that most of the time. We've already solved for the in-plane strains using that strain gauges. We know the basic material properties for our isotropic steel. Here's Young's modulus and Poisson ratio, and then our plane stress assumption. So our plane stress assumption says this is a thin plate. My sigma ZZ is going to be 0. My tau XZ and my tau YZ. So anything that has a Z as the subscript, either first or second. Remember, they're symmetric, so they're the same. All three of these are going to be equal to 0. Okay. So I've got numbers for these three, and then the opposite three subscripts. Notice I don't have an epsilon ZZ yet, but I got a sigma ZZ. So I have 3 of the stresses, and I have 3 of the strains. I want to get the missing ones using my Hooke's law. That's the idea. And then we can get the principles from there. All right, so let's see how that works out.
If I could just ask a quick question about the notation. You have epsilon xy versus tau xy. For example, what's the difference between those? I know that one is half the other, but what is the rationale for that?
Between epsilon and gamma. So gamma, from a physical standpoint, just represents a whole angle change. So if I'm starting here and say I got a parallelogram like that, this whole angle change right here be represented by gamma. Now, in the ideal cases, usually we see the parallelogram, something like this. We're going to apply some of it to the side and some of it to the front. But this whole angle, including this piece and this piece, it's just something that we could potentially measure. And it's visual. We know this is the whole angle changes gamma. When we put it into that 3x3, this is kind of our epsilon x face. We're on an x edge and we move up in the y direction, or we're on the epsilon y face, y edge, and we move in the x direction. So you might think about this half of it as epsilon xy and this half of it as epsilon yx. So altogether, they equal some angle gamma. That's something that's potentially measurable. But when we split them up into the two epsilon pieces, that's what it takes to go L epsilon L transpose if we need to rotate anything. So those formulas for transform are built on the state of strain, which is epsilon all the way around.
Thank you.
All right, so from the previous problem, we got XX, YY, and we've got gamma XY, as well as half of that being epsilon XY right there. So those are the things that we know on the strain side, all right? So I know these two, and I know this last one right here. Right. Basically, the first, second, and sixth entries, if we look at the Hooke's law in that 6x1. And then my plane stress assumption being the other one, I know these guys are all zeros, right? So I know sigma ZZ, I know sigma YZ, I know sigma XZ. Because either exact opposite places are what we know, right? So we're trying to find the ones that aren't circled. Right? Here's our Hooke's law. We got stress in terms of strain. We can write it either way that's convenient for us. Those are among the very last slides over in this deck. So all the way down to isotropic, there's stress in terms of strain, Hooke's law, and the opposite if we needed that in other. So we fill in our material properties. Those just sit right in there, and we can crunch those numbers. And we need to figure out what's what. Now, if sigma YZ and sigma XZ are zero, anything with a Z subscript, note that these are only linked by the diagonal entries right here. All three shears are like that, right? So I can see that this one's going to have to be zero because it only links to sigma YZ. That's sigma XZ is also zero, and it's only linked to gamma XZ. So I know that one now zero. And since I know gamma, I can calculate this sigma XY over here. It's only going to be linked by now. So now that I've got these, I've got everything I need except for epsilon ZZ over here, right? So to get our epsilon ZZ, we can take the Hooke's law right here. This is equal to these and these right here. Or I could see sigma ZZ right here is going to be related to the three normals, and that just goes across this third row right here. Right? I already know XX, I already know YY, and I know this one has to be zero. So using this third row equation, I can solve for epsilon ZZ. So this right here is just the third row of the Hooke's law equation. It's this piece right here. We know sigma ZZ is zero, so we calculate epsilon ZZ, and it works out to minus 214. So now I've got this one. So we're just kind of filling in the missing pieces one at a time. The shears are the easiest because they only link to the same subscript. And since we know two of the three strains, and we know the third row value, sigma ZZ, we can just go across there and get the one missing strain, which is epsilon ZZ. So this equation right here comes right from the third row of the Hooke's law. I think that's also listed as a shortcut in the plane stress slides. You'll see epsilon as a ZZ as a function of the two in planes. Zero on the left means we can cross this off, and then we just have XX and YY with those news, and then the ZZ we move to the other side becomes this right here. Divide through. So now I've got all the strains, and I can just multiply the 6 by 6 times the 6 by 1, and we'll get the stresses that we don't know, these in-plane stresses right here. So there's our in-plane state of stress. If we want to throw it in 3 by 3, remember I go down the diagonal, up and left. It's how I go top to bottom. So this void going down here is down here. Then the next two are up here. And then this one's last. That's how I like to remember it: down, up, left, or diagonal down, up, and left. That's going straight down here. Or you could say XX, YY, ZZ, no X, no Y, no Z for the shield. However you want to remember that's fine. Our epsilons, we'll peel them off and remember to split gamma into these two pieces, right? Now to get our principal stresses, we're already in a principal straight, so we can use the shortcut or always the eigenvalues. So we get 46 and minus 25, and the third one being 0 because epsilon ZZ is principal. As long as we see a row with no shears, that's principal, even if the normal is also. And then for principal strains, we can take the shortcut right there and get our values. Epsilon ZZ is a principal, and then the other two come from a shortcut. Or also note that when our material property is good in any direction, it's also good in the principal direction. So once I find these principal stresses, I could put those into Hooke's law. So over here, let's go a different color. If I put P1, P2, and P3 instead of X, Y, and Z, I'll get epsilon P1, P2, P3. So this is good in all directions. It's also good in the principal direction. So if I have the principal stresses and I don't want to run those shortcut formulas, if maybe I've already got Hooke's law in my number crunching, I can grab them that way too. We'll come out the exact same three numbers, shortcut formula, or we take the principal stresses and just use Hooke's law, same three directions, and get our principal stress. Anybody have any questions on that Hooke's law problem here? All right, let's finish off our last stress and strain problems, and then we'll take our break. So number 8 here, we're looking at a fuselage panel on the side here. We've got a plane stress, of course, fuselage panel's thin, and it's a reinforced fiber. So we got fibers running around the hoop direction. And then our two perpendicular directions, Y and Z, are going to look the same. All right, so we got a transverse isotropic condition. The fibers make it stiffer in that hoop direction, so we got 40 million PSI that way, and Y and Z are both going to be 30. So we can go back one slide to the transverse isotropic. That's an orthotropic, basically where Y and Z are going to be the same. Here we get. There we go. All right, so our Y going to work out the same. So we just take our orthotropic right here and put Y and Z as the same subscript. It's basically all we're doing. So here's the transverse isotropic. We just plug and chug all those material constants. And we've got two loads going. We've got a small hoop load of 700 PSI. That might be from a light pressurization. And then we've got a shearing. That shearing could be the lift from the wings minus the weight and downforce from the tail. So we get some downforce on the tail there, plus the weight at the back of the aircraft, and then the lifting force here. So that could produce this kind of shearing up on this side of the panel and down over here on the back side. So here's our two basic loads. We got a weight shearing and then a light pressurization load. So we can throw that into our state of stress. We know everything about the state of stress. It's a thin panel. So those three Z components are 0. We got the XY shear. We got the XX or hoop direction shear, and no axial load that we're working at this time. Right? And then we just plug in our specific subscripts. Remember that we don't need every single one of those news as long as we have enough to solve the diagonal, understand? And it's just a mirror image. So new yx over ey is the same as new xy over ex. So we just plug those in and we do one of the diagonals or the other. It works out as a mirror image. We plug and chug, and then we come up with our state of strain right here. Principal strains. If I look at the three Z components right here, the shears are 0 on Z. So this is a principal, and that means that I can use the in-plane shortcut. As long as Z is a principal, these are good. Or you can use the eigenvalues, also good all the time. Max in-plane is going to be the two that came from the shortcut, or whichever one is not epsilon ZZ. And we get max in-plane shear 24.6 microstrain. Absolute max, we just compare those three and whichever is the biggest. It happens that our ZZ is the middle one, so the in-plane and the absolute max will be the same. Only difference in the max shear stress and max shear strain is because this is doubled from the 3x3, and these formulas come from the 3x3. We don't see the divided by 2. All right, any questions about that orthotropic type material? All right, let's look at our last one, and then we'll go to break. So here, we're looking at a standard missile. Got 3 stages, and then the kinetic warhead there. And we've got our dimensions before launch. We get 5 Gs during the initial launch phase there. We're going to put drag right up there at the nose. We've got our inertia forces listed. So I just took the rough weights and multiplied them by 5. And here we've got, so this is the loads we're going to have on here. Areas are going to be constant cylindrical for the first 3 stages, and then it tapers like a cone. And we just want to look at the axial stresses and strains, all right, so that we can work our way to deflection. So the first thing we got to do is some free bodies. We need to take a little slice here, a slice in here, a slice in here, and a slice in here between each load and figure out what our forces are going to be in each body, right? So on the top, obviously we'll keep the top. Force in number 4 is going to be just the drag load, so 1,000 pounds compression. In stage 3, we've got the drag plus the kinetic warhead weight combined, so we get, I didn't put F3 in there, but that should be the 1750 compression. 3 there, and the other answer will come out. F2, we've got the top or the bottom. It's an equal number. I could do the stage 2 and the thrust, or I could keep the top pieces as well. Only 2 loads there to deal with in that stage, so I'll probably keep the bottom shorter. And then in the first stage, if I cut it, I might as well just use the thrust, 16,000 pounds. And for F3 in here, we're talking about the 1,000 of drag plus the 750, so minus 1,750 for F3 here. I do a lot of copy pasting in MathCAD there, so you can see I just forgot to change the subscript. So let's go minus 1,750 right here. And then 6,000 and 16,000. So everything's in compression, like we'd expect. The missile's accelerating, and the only positive force we got is the thrust pushing it from the bottom. Now, our stress, sigma, just F over A, right? For simple axial case. So now I know what the stress is, and I'm trying to work to get displacement. So I need strain. Strain is going to be sigma over E. So that's going to be essentially F over AE, right? So F over AE gets me my strain, and I know that my displacement, this is change in displacement with original length. So if I integrate that epsilon down the length, I'll get my change in length. Change in length per original length, and I integrate it over the original length, 0 to L. That'll get me to my displacement. Now, in 3 of these cases, stage 1, 2, and 3, F, A, and E are all constant, area being the one that could change in stage 4. A1's constant, A2's constant, A3 constant. So essentially those come out, and it's just integral dx or length 1, length 2, length 3. So FL over AE is my displacement as long as F, A, and E are constant. So I get those 3. The only one that's a little tricky is this 4th area. it's tapering like the nose cone is doing. And we've got this shortcut for integration. So we can just plug and chug on that one and we get our displacement in the nose cone, right? If we add all those up, there's my total change in length, and the final length is going to be the initial plus the change, and then we're going to minus on that. So it only shrinks by a little fraction of an inch with this casing material, which we've got aluminum thrown in there. Case. Okay. If we want the stresses, we just go back to this F over A. I didn't ask you for stress in 4 because note that's area is changing in 4. So it'll be different all through the length. But for 1, 2, and 3 with a constant hollow cylinder cross section, we're going to get the same stress in all places on those first 3 stages. All right, so here we exercise our force and stress relation, force per unit area. We used our really simple 1D Hooke's law, and then our strain displacement relation, du dx, and we integrated up to get displacement, integral epsilon dx. Anybody got any questions about that one? We tried all our formulas, but on a simple axial loading. All right, let's take our go ahead and take our break. We'll come back at 1/4 the hour, and we'll go over those beam homework problems.
One question about this one.
Yeah.
So your epsilon is sigma over E.
Right. So that's
So
our simplest 1D from right over here. Epsilon XX 1 over E sigma XX.
okay, you said you don't need any Poisson's ratio for that.
No, because we only have axial loading, so all these other stresses are 0. So
Okay.
that's still in the Hooke's law, but we only need the 1-1 term.
Okay. Yeah, I see. Got it. That's it. Thanks.
And we're back. All right, so now we're going to run through those beam problems, get a chance to exercise all of the various formulas that we came up with over the past few weeks. So first problem here, we're looking at a shipboard crane system. It's cable crane and it's mounted to a T-beam, so the T-beam becomes the railing for the crane. Bonus points if you notice that I Salvador Dali'd it a little bit here and went into a parallel wall with that pin. But nonetheless, still a pin connection, so we're going to have no moment on this left side and no moment on this right side. All right. So we want to figure out what's the max tensile and compressive stresses. For that, we need the max moment, and then max transfer shear stress. We're going to need the max shear force for that. So here's our free body. We got 10,000 pounds, 2/3 of the way over. So the closer side is going to get the bigger one, 66, 67, and then 33, 33 over on that left. And if we think back to our basic beam volume element, going to be right here on the early side. So here's our volume element. If we keep that same sign convention that I used, V down on the right, V up on the left. So that left side reaction, 33, 33, matches the volume element. It's going up. So I'm going to put positive 33, 33 right at the 0 spot. And on the right side, my reaction's going up, but positive V is down. So I'll put a negative of that RB reaction over here. And then we also know that it's tied to the derivative of V is tied to distributed force. There's no distributed force, which means my shear force doesn't change in between those loads, right? So I just take that 33, 33 on the left and I pull it straight over to the right. I take the 66, 67, pull it straight over to the left from each end. And at some point, it's got to make that jump. And where it makes that jump is conveniently right at the applied load. So here's going to be my shear on the right 1/3 and on the left 2/3. It's going to be this value. And the height of that jump, sure enough, is 10,000 pounds. Right. We talked about the reason that jumps downward, even though positive is down. We said that just before, right before that spot, here's my V, and it's got to oppose all of that RA right there. When I get just barely past that spot, I've got RA going up, but then I've got the 10,000 going down, which is helping going in the same direction as V. Right. So when I get just past this line, V is now going to be the 3330 minus the applied load, which is 10,000. So that's how it jumps from this number to this number, just on either side of the 10,000. And the height matches up. So what I like to do is, if you're doing it visually, just work from the two ends. We know the reactions and draw it across to the midpoint. And which way it jumps will take care of itself, as long as we get a height of 10,000. Now, we also know that dm dx equals minus V. So I can look up above and get the slope. I know the slope on my left 2/3 is minus 3,300. I know my slope on the right 1/3 is positive 6,700. And the other thing I know, because we've got the dolly pin over here and the standard pin over here, I know my moment is going to start and end at 0. So I can do this point and this point. And I see here's my slope with a sign flip. So I draw a line going up with a slope and this one down with a slope. All right, both hitting 0 at the ends. My M max is going to be the slope times this 6-foot distance, or this slope times the 3-foot distance. If we do the left side, there it is. So slope times distance, or slope times run, gives me my rise or fall. This delta between M on the left and M at the applied point is also equal to the area, because remember, this is the derivative of moment. So if I take this area, also 3333 high times 72 wide, there's the magnitude. And remember, it's minus the mdx equals v. So this area with a minus sign gives me this height. Let's put that in a different color, maybe blue. This area with a minus on it is this delta, or height, right? Because this is a derivative for that one. minus dmdx equals v. We've got that relation right here. So that means delta M is minus of the area. So here we are using that. If you just want to go with the graphical approach, this area, slap a minus on it, is this height change. And we changed height down. So about 240,000 with a minus sign. That just means that it's curling in at the top. Just a sign convention goes opposite the M where we draw curling in at the bottom. So we've got Vmax and we've got Mmax from our shear and moment diagrams. You can also take a slice here and use statics to get those M of X and V of X equations. That's fine too. Or we can do a pure integration approach up from P of X equals 0. And then use the boundary conditions. V at 0 is 3333 and M at 0 is 0. Integrate up. So 3 ways we can do it. I went ahead and showed you the visual or graphical approach. Now, for our cross section, we got a T-beam, so we know it's centered left to right. I got one symmetry axis, so I know my centroid's in the center left to right. I just need to find where it is from top to bottom. So I cut it and I kept the whole flange and what was left as the web. So I got a 12 by a half and then a half by 6. My height from the top for the web is going to be 6 inches down and the other one's going to be 12 1/4 down. And then we just take the weighted average. So the centroid 8.08, about 2/3 of the way down. And that makes sense because we've got more area at the bottom than we do at the top. For an I-beam, we should get it right in the middle. In fact, we don't have to calculate it. But we've got a flange on the bottom, none on the top. So the centroid should be further down. So that passes our sanity check. Moment of inertia. Well, we've already got those Y bar 1s and 2s. We might as well take advantage of those. We can get dy1 and dy2. And then our area moment of inertia, that's going to be about the origin. So we take the BH cubed over 12 for each piece, plus A times dy squared for each piece. IZZ comes out to about 150, and that's 4th order inches. And then our bending stress, just minus my over I. That's with M curling in at the bottom. Now remember, our load is going curling in at the top. So I should expect, for sanity check, a negative number at the top and a positive number at the bottom with the moment going against my sign convention. Right? This is the way my moment's going. It should compress in at the top. So I'm expecting a big compression number. If Y is positive down, I just go up that Y bar distance. So minus 8.08 is the Y component or coordinate at the top. And 4.4, 12 1/2 minus that Y bar gets me the distance from the centroid to the bottom. Right. So I'm expecting if I plug these two numbers in to this formula, I should get my compressive max with this one and my tension max with that. Just because I know the moment is curling in at the top. And if I plug and chug, sure enough, I get 7,000 on the bottom, tension max, and compression max of 12,000 on the top. Now that means my biggest magnitude is the one on the top, and that does make sense because I'm farther away from the centroid. My over I, my Y distance is farther. This happens to be a compressive number. But it's farther, same moment, same I. So I get negative 12,000, and I get positive 7,000 because it's a little bit closer distance to the bottom of that flange. All right, any questions about the bending stress part? All right, for the shear, VQ over IT. And remember, Q, we get a choice for our area star and Y star. We can shade from the top or the bottom. I said, you know what? I'd rather do one piece than two, so I shaded from the top. If I shade to the centroid, I'm calculating the stress however far I shade to, from the bottom up or the top down, but it's good on just this line right here. And it always works out that the maximum is across the centroid. So basically along that Z-axis is our max shear. So tau max, I shade down there. I just have one area. It's half of the Y bar height. Gets me the distance between the big centroid and the shaded centroid. So there's Q. My thickness is whatever the thickness is at the shaded line I draw across. So that's going to be the 1/2 inch, the web thickness. I is the same, and we grab the same V max. So we get minus 1450. Note that that minus just means that the stress is really going up. V's positive down, tau xy is positive down, and we got a negative, just means that the shear's flowing up in that section. All right. Anybody got any questions about the transverse shear? All right, let's go on to the second problem.
Yeah, question.
Yeah.
So for that Q term, is there a name for that? How am I to understand what that Q means?
Okay, so the Q itself comes from our non-uniform bending derivation. That one was right here.
Yeah.
Right, so I don't know, for some reason I'm having it jump pages. So right here, Q is essentially integral YdA shaded from the edge up to where we want to look. On our model here, our little volume up, we shaded from the bottom, and we're looking at this slice of however far up we shaded.
Okay, so your tau is changing with your Y.
Yes, it changes with Y position. And
Okay,
it's
so
always
then
it's
then
Y
to
on
get
the bottom
max,
and Y on the top.
got it. So to get max, you got to go from either the bottom or the top to the middle.
To the yeah, whatever the
To the
central.
centroid, yeah, not the middle,
So
sorry.
this Q is just integral YdA of however far up you want to look.
Okay.
Just like I is Y squared dA. All right, so it's just a letter that takes a shortcut of a plus. Now, because we're dealing mostly with polygon shapes and rectangles especially, I could say this YdA is really just a summation of shaded areas times distance between centroids of those shaded areas.
Mm-hmm. Okay.
So for our case right here, if I shade from the top, I only have to deal with this one rectangle, this one right here. And I can easily find the centroid of one rectangle. And then the Y star is shaded centroid to big centroid. Or if I'm doing a sum, it's going to be all those A stars. So if let's say I shaded from the bottom, I'm going to have a 1 and a 2. And then I'm also going to have, let's change the color. Red. If I shaded from the bottom, I'd have this piece. So a star 1 and a Y star 1. And I can pretty easily come up with this distance to the big centroid. And then I'd have this web piece right here, and it's easy to find the center of a rectangle. So then here's my Y star 2. And I just add those two up, and that also gets me Q. But I might as well, if it's an I-beam, it doesn't matter. You shade from the top or bottom, you get the same. But in a T-beam, you might as well take the side that only has one piece.
Yep. Okay.
And
All right. Yeah, got it. Thanks.
So just for clarification, the reason we find that midpoint in the first place is because that's where we expect the maximum shear.
Yeah, the maximum shear will always work out. So when you think about this, if I don't shade anything, my centroid of the shaded is sitting on the end. So Y star becomes the biggest it can be, but area is 0. All right. If I shade the whole thing, I get the biggest area, but my Y star disappears because the centroids land on top of each other. The shaded area is the whole area. So it just works. It always works out that, in one extreme, this one's 0 and the other one's this one's 0. And if you shade down to the centroid or up to the centroid, you get the balance of this product being the biggest. Does that make sense?
It does, thank you.
My two bookend cases, no shading, and Y star is big. That's this distance, but there's no area. And then in the other case, if I shade everything, my area is big, but my Y star is 0. It's the same centroid right here to right here. There's no change in distance.
And so the reason that we're looking for that particular area is I'm just thinking you have free face on the very top, free face on the very bottom, so there's no shear stresses there. Centroid, I'm assuming, that's an inflection point between the compressive and tensile stress. So really that shaded centroid is where you're going to be finding the max. So
in a rectangle, your stress distribution looks something like this. The biggest is in the middle. It's zeros at this end, gets bigger at the centroid, and then gets smaller again and goes back to 0 at the bottom. And it's a similar look for this one. This one will start at 0. It'll come up in value, and then it'll actually take a dip right here because the width is bigger. The T changed, and then it goes back to 0 at the bottom. Maybe I'll make a purple color. So it's going to start at 0. It's going to get up big. Then it's going to take a dip because thickness changed from a half to whatever it was, 6 inches. And then it's going to dip down to 0 at the bottom again. All right, any other questions on that transfer shear? All right, let's go on to the second one. Here we've got chipboard crane. No, that's problem number 1. Let's go to the next one. We've got an angle iron, and we're supporting towed instrument array. All right, so we've just got that rigidly connected onto the superstructure, and it's perpendicular right there. So we've got a fixed end, and we've got a free end. No reactions over here on this outward end. And then we've got a little bracket holding on here. And because of the drag in the water, we're going to get an angle on that cable at 30 degrees. And the tension in the cable we measured at 500 pounds. So this one is going to be unsymmetric bending. We're not symmetric on either axis with an L bracket. It's the simplest unsymmetric shape we can have. But we are going to have to find the centroid in both directions. And then we need to find that neutral axis. Where does that complex bending stress equation equal 0? And then we're also going to need our bending moments about y. So let's take a look at how this sets up. First thing, easiest thing to do we want to do is probably the statics. Right? So on the front face here, I've got a positive moment going this way. And on the back face, a positive moment about z would be going this way. It may also help to draw this in a pair of 2D sections, all right? So I got the 433 down here. I've got no moment over here, no moment here. And then I've got my reaction moment in the sign convention will be positive back here. So we just need to solve for this one. Going to be that force in Y, the 433 pounds, and times the length. All right. So that one's probably the easier one to look at. We get just about 16,000 inch-pounds reaction about Z. Now, let's look at it from the top. And bear in mind that my Y is down. So I'm going to put Y-axis going down. So we're looking down from the top of the page right here. In this one, I have 250 pounds going this way. And my moment about Y, down on the positive face. So it's the sign convention is going to look the same as the side view, but my moment about Y will be this way. If I point my thumb into the page, positive Y is this way. And then same thing, I got to go negative Y direction, so I'm going to point my thumb out on the left side. So MY and MZ from these side and top views has the same curving direction. And I'm going to solve this. Here's my moment about Y. It's on the back face, so it goes against Y. I stick my thumb opposite that inward arrow. And I can see 250 times length is going to go the same direction as MY. So MY ends up with a negative sign and a magnitude of 9,000. If the isometric is a little tough for doing those moments, just break it into 2 views. A side view, like we drew above here, and then a top view looking straight down. So we only have to deal with one of the forces at a time. All right, the force that's in the page. All right, anybody have any questions about how we got those 2 moments?
I guess I'm still a little bit confused on why MZ is positive.
All right, sure. So let's jump over to our original sign convention on probably the second slide. So here's our 2D convention. On the front face, we're going to follow exactly the X, Y, and Z directions and exactly the opposite on the back. That's dry erase, so it will come off hopefully eventually. All right, let's look on the front. Here I've got X, I got Y down, and I got Z in. Okay. I'm going to draw it isometric just so Z is real clear. Right. So front face, I put my thumb in that Z direction, and here's my moment. So M about Z on the front, gonna go like this. On the back face, or anything where we're pointing out in the negative Z direction, this is the minus X face on the back. So my minus Y goes this way and my minus Z comes out this way. So on any back face, as in going in the negative X direction, I'm going to stick my thumb in this negative Z. So that's going to go like this. And this is also moments. If I look at it from a just an XY view, X and Y here, remember Z's into the page. So thumb down here, there's my MZ on the front, and thumb opposite Z, or in the negative Z direction, on the back. So here's my MZ here. So looking at it from the side right here, here's my 2D view. Now for a moment about Y, over here, my Y is down. So I'm going to stick my thumb in the downward direction. I got to make sure I don't torque my hand off here. Thumb in the downward direction, and I'm going to curl this way. So moment about Y, I'll do it in green. This one. And then on the back side, I just put my thumb in the negative Y direction and curl. That's going to be coming around this way. Moment about Y here. So let's look at it just from the top. So in the top view, I've still got X going this way, and I've got Z going this way. All right. And over here, I've got Y down. So here in the 2D, I stick my thumb in that into the page direction and curl like this. Here's going to be my MY on any front face. And on any back face, if Y is positive in, negative Y is going to be positive out. So here's my back face. So this is a top view, MY. And here's my side view for MZ. And all you have to decide is, am I on the front or the back? Am I pointing in the positive X out of that face, or am I pointing in the negative X? And same thing with the moment about Y. Does that make sense?
Yeah, I think that clarifies it. Thank you.
Okay. If anything ever starts to get confusing in the isometric, just draw it one view at a time. All right. We've got a load in both directions. We've got a Y load and a Z load. Right. So if I look at the top view, I don't have to work this load in Y is not going to cause any moment about Y. So I only really need to look at the Z force. And then if I'm looking on the side view, my force into the page can't cause a moment about Z either. So I can just concentrate on that force in Y in this picture. So force Y gets me my Z moment, and the Z force gets me my Y moment. All right, so let's jump back and see how this plays out. So now we got those moments. We're going to use our asymmetric bending. On the second slide, we've got the way to calculate those centroid positions. That's just a plug and chug. I cut it and kept the whole web and took the rest as the flange. But you can cut and keep the whole flange. You'll still get the same answer. Y bar comes out 3.95, Z bar 0.548. Always good to do a sanity check. Our total height is 6, and we have more stuff on the bottom. So we came out 4 out of 6 downward. That makes sense. All right. Our total width is 3, and our centroid was only at 0.5, and we got more stuff on the left than we do on the right. So both of these numbers are same numbers. Then we got dy and dz. We can just take the y bar for each piece minus the whole y bar, and z bar for each piece minus the whole z bar. And now we can get our moments of inertia. Those are also just plug and chug. BH cubed over 12 for IZZ, and height times width cubed over 12 for IYY. And then we use the area times D for each pieces. Area times D squared. Right. So IYY comes out 0.795, 4.3 for IZZ. Note that because we're taller, we're expecting a bigger moment of inertia bending this way. We got more height to resist this bending. Over here, if we're bending about Y, we've got less width. So we expect a smaller IYY. It's going to be easier to bend about this axis than it is about the horizontal. So those are also same numbers. And remember, IYY, IZZ can only ever be positive. IYZ is the only one that can have a plus or minus sign. Just happens to work out because our pieces are going to be in quadrant 1 and 3, right? Centroid for this one is in the first quadrant, positive Y and Z. And here we got a negative Y and a negative Z. So because those multiply together, dy and dz, everything came out plus for this. And that's just however it works out. You might have a picture of whether plus or minus is same, but not all. Then in order to get our neutral axis, we take that long sigma xx formula that includes both bending axes. That's this guy right here. And we set sigma equal to 0. We solve for the slope, some y per z. So there's that formula. It's an inverse tangent. Comes out minus 82 degrees. Now remember our net bending moment, because we could see exactly the breakdown. Our net bending moment is across about this angle, right? We got 433 down and 250 this way. Our net force is going about this direction. And that means our total bending moment, including the y and z components, is about this line. So we want to come up with something that's in the same quadrant, okay? Because of the asymmetry of the shape, if this were a fully symmetric shape, it would line up with the net moment axis. Well, we can see it's skewed a little. There's a 30, that one's at 83. They're in the same quadrant, so it's still a same number for us. And I can see based on the moment bending here, and this being the 0 stress line, roughly I should be in at point B or compressive, and I should be out at point A. Or tensile. So here's our locations for A and B. They're just going to be the total dimensions minus the centroid for B, or the negative of the centroid locations for A. So there they are. And then we plug and chug on the stress formula. Comes out 10,000 psi at A, and it is positive. And here we're coming out this way. That makes sense. Out for bending here, and the bending arrow goes in at the bottom. So here we are at B. Remember, you just need to take a ruler or a straight edge from that neutral axis. Say I'll make that one green. Here was what we calculated for 0 stress, and I want to go as far away as I can. I see the last thing I hit is B, and up here the last thing I would hit is A if I slid a piece of paper or a ruler parallel to that neutral axis. So those are the last two spots. We're not really sure exactly which is further away if we just glance at it, but I can see by this, and perhaps by not drawing to scale, that B is a little bit farther away from that green center line, the neutral line, because its magnitude is bigger. It's compressive, but it's 26, and this one's 10. So it just tells me A is a little bit closer to the centroid neutral axis, and B is a little bit farther. And in factor safety, we just divide through the biggest stress by underneath the yield, and we see we're about a 2-to-1 factor safe. All right, anybody got any other questions about that? This gave us a chance to practice 3D statics, but we can break it into two planes. We can look at the XY plane and the XZ plane and just get the two component forces and the component moments pretty easy. And our sanity check checks out okay. I can see the bending has to be perpendicular to this guy, right? So my bending I know is going to be like this, which has got to be in here at B and out at A. All right, let's take a look at number 3. We got a crane hook, easy square cross section. And like most crane hooks, we're going to be tensile axial force here at this section A. This is as far away from the load as I can. So my bending moment is going to be as far away, gives me the biggest bending moment right there. Right. And we got a nice plug and chug for that curved beam formulation. My R bar is, of course, just in the center. I get my moment using the R bar. So tensile force of 1,000 pounds. I can just do that from statics. And then I can also see my moment with the positive sign convention curving into the center, minus 45. So that just tells me that I'll be tensile on the inner edge and I'll be compressive on the outer edge if I can get back to pen instead of the mark. Okay, so we're expecting a tension out inside and a compression on the outside. And then we just plug and chug. My neutral axis is always a little bit inboard. So there's 4.481. We take the axial stress. Remember, that just shifts my bending curve up or down. It's going to shift it out toward the positive. And here's my bending one. And bending is going to look something along these lines. All right. The bending stress goes through zero because at capital R equals little r, this second term goes away. But remember, we shifted up just a little bit with the axial stress. So 1 KSI shift up. It means our actual 0 point is just going to be a little bit outboard because of tension. If it were compression, our 0 point would come a little bit on the inboard. Bless you. And then factor of safety, 3.3. We should always get a little bit smaller number at the outboard, whether it's tension or compression, and a little bit bigger number on the inboard from the way this 1/R formulation skews. All right, for number 4 here, we're looking at a cantilever beam. It's also got an additional roller support. So very same boundary conditions that we dealt with in class. Same kind of thing, fixed plus an extra roller. We've got an applied moment and we've got a distributed load this time. So the superposition way first, we can break it down into the distributed plus the end moment. And then our last condition would be replacing the roller with a vertical force. And if, like we think, the reaction is going to be up, we could say F equals minus RB because F in the 3.5 slides are down. And then we just grab those verbatim from the cantilever formula. We can also get those from eFunda or Engineer's Edge or whatever handbook we like, but here they are. And our superposition tells us that 1 plus 2 plus 3 is good for everything, including my displacement on the end. And that's what I know. I took away that roller and replaced it with a force. So I enforce this boundary condition right here. That lets me solve for the extra reaction. We get 3/8 of the distributed load times L, and then 3/2 of the moment on the end per L. Now for the rest of that, once I know what that is, I can just plug it in for the force and the reaction here and right here, and I can get the other 3 items, the reactions on the left and the rotation on the right. For the integration method, we just start with this fourth derivative. For us, it's a constant, P naught all the way across. We come up 1, 2, 3, 4 times, and we just need to enforce our boundary conditions, right? So on the end, we got our reaction. We don't know what it is, but we'll solve it later. We come up again to moment, and moment on the right is equal to that applied moment, M naught. So we solve for C2. Then we come up again. We know V prime on the left is 0, so we can enforce that. Gets a solve for C3. And then V at 0 on the left lets us solve for that fourth integration constant. Now at this point, we still have one thing we don't know. This guy, R at B, is a question mark, and that's where our extra, the one we used in superposition, also comes into play. V at L is 0, and we'll get the same stuff for R. Now there's a lot more chance to mess around and miss a plus or a minus or a chain rule and exponent of integration. But we can see we get the same stuff. Now on the plus side, we get the formula all the way across instead of just the endpoints with our superposition back up there. But if the superposition has V of X for each individual case, you can also add those, right? And we see we get same answers for all that stuff. Any questions about that? All right, for number 5, we're looking at a sandwich protection system. We've got metallic layers on the top and bottom. That's going to take the big stress loads for us and also any kind of shrapnel type loading. And then we've got a blast loading 25 kilonewton per meter. Because it's a big dynamic load, we need something soft and energy absorbent in the middle. And that's what the resin core is going to do, is absorb that vibrational and dynamic energy. So this is very typical composite panel, something strong on the top and bottom, or more expensive, and a little slice of it and then something softer and or cheaper on the inboard edge, which can handle the shearing and energy dissipation, but doesn't necessarily need to take the biggest bending loads, which are going to be way up here and way down. So we have that composite flexural rigidity. It's E times I for each section. We got 2 of the top and bottom aluminums, 1 resin in the middle. I for the aluminums does have a parallel axis component. The resin does not because it sits on the central, that middle rectangle. Don't have to do an AD squared for that. So we got 10 million Newton meters squared. Our free body diagram here, I can put a, I see my equivalent force is going to be right at the center. So I should get a max at the center for my bending moment. P of X is straight across. That means V is a straight line all the way through. And same reaction on both sides because equal reactions. So from positive to negative in a single slope. And then my bending moment's going to go from downward max here, upward max here. And note the bending moment max is where V, or the slope of moment, is 0. So that's going to be right and center. And I can either take this triangle to get this height, or I can take the right side triangle. And they're the same size. We could also just do it with a free body at the center. So bending stress minus My over I, but we've got an EI on the bottom. So we just add the E for the specific material on the top. I can see I get in the resin. Remember, I can only go as far as the material. So the resin goes to 150 millimeters, plus or minus, and the aluminum goes to 160. All right. So a bigger modulus and a bigger Y distance makes this number significantly larger. We see this does the job of holding the bending. The resin takes less of the bending stress, but it can absorb energy because it's more compliant. So pretty much a plug and chug. It looks very similar. We've just got an extra E in the bottom, so we have the extra one on the top as well. And remember, only goes as far as the material. So I have a sub resin here and a sub aluminum to remind you of that. All right, let's take a look at our very last one. We got a flight deck section, 7-foot frame spacing. So we've got a couple of transverse frames here. And we're looking at a section of flight deck. Into and out of the page looks like this. So if we slice into the page, this is what we get. 2 stiffeners in the long direction. And we've got all the dimensions. Everything 1/2 inch thick for simplicity. And here we're looking sideways on the ship. So we'd have a big T stiffener here and a big transverse T right here. T's are good for bending, but not so great for torsion. So we're going to assume that it can not move, but it can rotate. So our bending would look something like that. We're assuming a simple type support. So we see the little pin roller there. As we said, T's are not very torsion resistant. They're all pretty close to the radial center. So we can figure out IZZ for this and then get our maximum stresses. So P of X is straight across, 8 pounds per inch. That also tells me my shear line is going to be that slope all the way across, -8 the whole way. Reaction A and B, we have a little bit more on the right than on the left, just because the toe tug is sitting 4 feet out from the left. So I get those 2 reactions, and that gives me the ends of my curve, right here and right here. That's all I need. And then I take that -8 slope and I go from here to here. And sure enough, when I hit the applied 600 pounds, goes from 209 to -391. There's my 600-pound drop. So we don't have to do any work at that middle. Just come from the ends and then drop or jump or drop line right at the applied load in the midspan area. And this one gets a little bit dicier. We've got a big negative slope to a lesser negative slope, and then a sharp change. So this is not a smooth line. There's a sharp point right here, and then it goes to a bigger slope. So curving, second order, and then a sharp turn this way. And my height there is either going to be this area or this area. They're both trapezoids, so pick your choice, and that magnitude is going to be this height right here. You can also get it from statics. Remember, multiple ways to do it. Same deal to get Y bar. It's going to be closer to the top. because we got the deck up there and the flanges are just 6 and 6 and the deck was 30 inches wide. So it's gonna be closer to the top. Here's our IZZ, and then our max compression from the bending formula, we see we had a negative moment. So we're gonna compress in at the top, minus 106 on the deck and plus 182 on the flanges. Right? We're closer to the top than the bottom, so this is smaller and this one's bigger, and we're curving in at the top from the negative moments. Anybody have any other questions about the beam stuff? Okay, so the plan is, you're welcome to come in, not come in. I'll verbally go over the instructions, but I'm also going to have them paste the written inside, and it will pop up just like the assignments do, just like the homework. So it'll be in there, and when you're done with it, you can just upload it. For the in-class folk, if you're not doing an alternate time, just upload it the next night by Thursday, 23:55. I think I've got it set on. If you're taking an alternate time, it's set to accept at a rolling interval. Just download it and take 24 hours. All right, so if you want to come in, you're also free to work it in class if you want to ask a question or something while you're here. It's only designed to take an hour, so don't think that it's one of those take homes it's supposed to take 24 hours to do. It's just a regular test, but I find people are less stressed out if they, have a leisurely time to take it.
Okay, can you say that again? When are you gonna post the exam?
So it'll open up first thing Wednesday morning, I guess 3 a.m. Eastern or 12 a.m. Maybe it'll be 4 a.m. Eastern time. And then if you're going to take it if you're remote, just download it and take 24 hours or give or take and just re-upload it. So you'll upload it just like you would the homework. Yeah.
Okay.
And it'll be right over here in the assignments. I got it programmed to open up. Yeah, at 12 a.m. That's probably Pacific time.
Okay.
But it will accept after the student. So if you're on an alternate time, just email me about that. Download it whenever is convenient and take 24 hours and don't blame it.
Hey, sir, this is Chris. I just had a quick question on number 3.
Yeah, sure.
Hey, I was curious about how you design the sign for the moment, like how you know which way it goes. Because I worked in, I got my moment the wrong direction, basically.
All right, so for number 3 on the curve beam, if we go to the curve beam formulation, just back at this little volume element, the convention was chosen that moment about Z curls in toward the center of the beam curvature. So this from the derivation is just the case. So the way you think about it, no matter which side you cut it on, left or right, a positive moment will curl in toward this center of the beam that's curving around.
Okay, that makes sense. Thanks.
Yeah. So if in doubt, always just go back to the little volume element, or in 3.1, it's on the 4th page.
And since it's getting pulled apart, it's negative.
Right, and that's typical for pretty much all the crane hook problems. In fact, I gave it a simple cross section, but what you'll notice in a lot of cranes is if you look at the cross section, it's kind of a teardrop. That's so that out here where there's tension, you have a little more width and beefiness. And then over here, where we don't worry as much about a material in compression often, it'll be a little narrower on the compressive side. So that's why you'll often see a crane hook, if you look at it closely, and so it's going to curve around like this. You'll see the beefier part is on the inboard edge, and from bending and the axial. So the bending this way and the axial goes out, so it gets double tension on that inside.
Okay, cool. Thanks, sir.
Yep.
Sure. Would be available around when we discuss some things related to the material from this class, but not exactly about this class.
Is that 1500 tomorrow?
let me